Black holes are not cosmic vacuum cleaners. They are nature's ultimate engines of impossibility. They warp time so severely it can theoretically loop back on itself. They stretch matter into an infinitely long strand, a process known as spaghettification. And they permanently erase information from our universe, directly violating the sacred law of information conservation. But what if everything you think you know about black holes is wrong? The strangest truth is not what falls in, but the fundamental paradox of what remains behind. When a black hole evaporates, what happens to the space it left? This question creates a direct conflict between general relativity and quantum mechanics, threatening to unravel our entire understanding of reality. This is the abyss that defies reality. To understand that paradox, we first need to understand the basic structure of a black hole. A black hole is a region of space-time where gravity has become so powerful that the escape velocity exceeds the speed of light. This means nothing, not even light itself, can escape once it crosses a certain boundary, the event horizon. The event horizon is not a physical surface, but a mathematical threshold in spacetime. Its size is given by the Schwarzschild radius, which is directly proportional to the black hole's mass. It behaves as a one-way membrane. You can enter, but you cannot leave. For the person crossing it, they would notice nothing special at the moment of crossing. But for an outside observer, anything that approaches the event horizon appears to freeze and fade away, its light redshifted to nothing. Inside the horizon, space and time swap roles. Time no longer ticks forward. Instead, it points directly toward the singularity. The singularity is a point of infinite density and zero volume, where our known laws of physics break down. General relativity predicts it, but in doing so it also signals its own failure. To understand the true nature of the singularity, we likely need a theory of quantum gravity. Despite their name, black holes are not empty holes. They are incredibly dense concentrations of mass. For comparison, a black hole with Earth's mass would be smaller than a marble. However, the average density of a black hole decreases as its mass increases. A stellar mass black hole, formed from the collapse of a massive star, can have a radius of about 30 kilometers. A supermassive black hole, with millions or billions of solar masses, can have an event horizon larger than the orbit of Neptune. At the heart of every black hole, regardless of size, lies an infinitely dense singularity. This simple picture already contains deep puzzles. The event horizon seems to seal off information, challenging quantum mechanics. The singularity pushes general relativity to its breaking point. These tensions suggest that black holes are not just exotic endpoints of evolution, but the key to a deeper theory of reality. This brings us to spaghettification, one of the most extreme consequences of gravity's gradient. Tidal forces arise because gravity weakens with distance. Near a black hole, this difference becomes brutal. If you fall feet first toward a stellar mass black hole, the pull on your feet is exponentially stronger than on your head. The tidal force across your 2-meter body can exceed millions of times Earth's gravity. Your body is stretched vertically while compressed horizontally, tearing apart at the molecular level. The term spaghettification, popularized by Stephen Hawking, captures this process vividly. For a black hole of 10 solar masses, the event horizon is only 30 kilometers wide. Spaghettification occurs well outside this boundary. You would be reduced to a stream of atoms in normal space before crossing the point of no return. Supermassive black holes flip this story. With event horizons spanning millions of kilometers, the tidal forces at the threshold are deceptively gentle. Take the black hole at the center of our galaxy, Sagittarius A, with a mass of 4 million suns. Its event horizon is about 12 million kilometers in diameter. At that boundary, the gravitational gradient is so mild that you could cross the horizon without even noticing the stretch. For a human, the tidal force there is less than 1/10,000th of Earth's gravity. This mildness provides a brief survival window that stellar mass black holes deny, but inside, the story changes. As you continue falling toward the singularity, the gravitational gradient steepens without limit. Eventually, the tidal forces become so intense that you will be spaghettified, stretched into an infinitely long strand of matter. So the crucial difference is location. For stellar mass black holes, spaghettification is immediate and occurs in the outside universe, visible to any observer. For supermassive black holes, you get a temporary reprieve, but the singularity guarantees your eventual stretching hidden beyond the event horizon, invisible to the cosmos. And while your body experiences this distortion, time itself begins to warp in ways that defy intuition. That is the next strangeness. Time does not flow at the same rate everywhere. Gravity slows time, and near a black hole this effect becomes extreme. The time dilation factor follows a precise rule. At a distance of 3 times the Schwarzschild radius, time runs about 20% slower for an external observer. At 1.1 times the horizon distance, time slows by a factor of more than 3. At the event horizon itself, the dilation diverges to infinity. For a distant observer, an infalling object appears to slow down, freeze, and then fade to black just before crossing the boundary. You would never witness the moment of crossing, but from the object's own perspective, its clock ticks normally. It crosses the event horizon without noticing any temporal anomaly. It continues falling inward, experiencing the curvature of spacetime as it approaches the singularity. Both descriptions are valid under general relativity. This duality is more than a curiosity. It creates a fundamental conflict. From the outside, nothing ever actually enters the black hole. The entire mass that formed it is still asymptotically frozen at the horizon, a picture known as the frozen star model. From the inside, matter has already crossed and reached the singularity, which timeline corresponds to reality. This tension between two equally valid perspectives directly challenges quantum mechanics, which insists that information cannot be destroyed. If matter never truly crosses, information is preserved outside. If it does cross, the singularity destroys it. This is the information paradox, one of the deepest unresolved problems in modern physics, and it emerges directly from the simple act of asking what time really means near a black hole. The information paradox rests on the assumption that black holes are eternal. In 1974, Stephen Hawking shattered that assumption. By combining quantum mechanics with general relativity near the event horizon, he showed that black holes are not entirely black. The vacuum of space seethes with virtual particle pairs that pop into existence and annihilate each other. Normally, this is invisible, but at the event horizon, gravity can rip a pair apart before they annihilate. One particle falls into the black hole, while the other escapes into space. The escaping particle becomes real radiation, carrying away energy. The infalling particle has negative energy, reducing the black hole's mass. The black hole is slowly evaporating. The process is unimaginably slow. For a black hole of a few solar masses, the evaporation time is about 10 to the 67 years, far longer than the current age of the universe. Supermassive black holes take up to 10 to the 100 years. But eventually, they vanish. This leads to a profound puzzle. Hawking radiation is completely thermal, encoding no information about the matter that formed the black hole. If the black hole evaporates entirely, what happens to all the information that fell in? Quantum mechanics insists information cannot be lost. The information paradox is no longer a thought experiment. It is a direct contradiction between two well-established theories. Resolving it will require a deeper understanding of gravity and quantum mechanics. The paradox is concrete. Quantum mechanics demands information is never destroyed, but black holes are blind to their own history. The no-hair theorem says they retain only mass, charge, and spin. Every other detail of the collapsing matter is lost to an outside observer. When Hawking radiation carries away the black hole's mass, that radiation is purely thermal, completely random, encoding nothing about what fell in. Information appears to vanish. Hawking's 1976 argument was direct. The radiation cannot carry information because it originates from quantum fluctuations near the horizon, unrelated to the interior. He concluded that information is genuinely destroyed, violating unitarity, the bedrock that the future holds all information from the past. He insisted this required rewriting quantum mechanics. Most physicists resisted. If information loss is real, cause and effect break down. The holographic principle offered a way out. Proposed by Gerard T. Hooft and Leonard Susskind, it states that all information inside a black hole is imprinted on the event horizon surface, like a hologram encoding a three-dimensional volume. Unitarity is preserved, but the interior spacetime becomes a projection. For decades this was speculation. The turning point came from the Page curve. In 1993, Don Page argued that if black holes preserve information, the entropy of the emitted radiation must follow a specific pattern. Rise, then decrease as information leaks out. No one could derive this curve from quantum gravity. In 2019, a team using the replica trick and quantum extremal surfaces computed the page curve for a simple black hole model. The curve matched. The radiation does carry information after all. These are simplified models, but they show the paradox has a resolution in principle. The deeper lesson is that spacetime itself may be emergent from quantum entanglement. Resolving the information paradox is not just about black holes. It is the clearest window we have into quantum gravity. At the center of the Milky Way sits Sagittarius A, a supermassive black hole 4 million times the mass of our Sun. Its gravity holds stars in tight orbits, giving us the most precise mass measurements outside our solar system. 5 billion solar masses. The Event Horizon Telescope imaged its shadow directly in 2019, the first picture of a black hole's silhouette. These are not anomalies. Most large galaxies host a supermassive black hole, with masses ranging from millions to billions of suns. Their influence extends across the entire galaxy. They launch relativistic jets that stretch thousands of light years, heating gas and preventing it from forming stars. This feedback loop ties the black hole's own growth to the galaxy's evolution, making them active architects of cosmic structure. The biggest puzzle is their timing. Quasars, highly luminous active galactic nuclei, existed less than 1 billion years after the Big Bang. These are powered by supermassive black holes that had already grown enormous. Standard accretion from surrounding material is far too slow to reach billions of solar masses that quickly. Something accelerated their formation: direct collapse of massive primordial gas clouds, or the merging of many smaller seeds. Supermassive black holes are not just gravitational monsters. They are essential engines that shape the galaxies we see. Understanding how they grew so fast in the early universe is one of the major challenges in modern astrophysics. The James Webb Space Telescope has found supermassive black holes existing when the universe was just 570 million years old. These are not small seeds. They already have masses in the billions of suns, fully formed. Standard accretion physics cannot grow a black hole that quickly. Something dramatically accelerated their growth. 5, with a mass over 1 billion solar masses. This object is one of several candidates from the CERS survey, all puzzlingly massive for such an early time. To reach this size so soon, the black hole must have either started from a massive seed formed by the direct collapse of a primordial gas cloud, or it consumed matter at an extreme rate well above the Eddington limit. The direct collapse scenario creates a black hole of 100,000 solar masses or more, bypassing star formation entirely. But even with that head start, reaching 1 billion solar masses within a few 100 million years requires near constant feeding at maximum possible rates. The alternative is super-Eddington accretion, where the black hole periodically exceeds its standard limit, growing in intense bursts. These findings reshape our understanding of cosmic history. The black holes appear to have formed before their host galaxies fully assembled. They may have acted as gravitational anchors, attracting the gas and dark matter that later formed the first stars. This suggests black holes are not just a consequence of galaxy formation, but a primary cause. The emerging picture is that black holes could be the oldest structures in the universe, predating galaxies by hundreds of millions of years. JWST is turning theoretical speculation into direct observational evidence, forcing us to rewrite the early timeline of the cosmos. Since 2015, LIGO and Virgo have detected over 90 black hole mergers, catalogued in GWT C-5, by capturing gravitational waves that stretch spacetime. The most recent event, GW 150,114, merged 2 black holes of roughly 30 solar masses each, producing a final black hole exceeding 50 solar masses. KAGRA, the Japanese detector, now works alongside them, improving localization for future events and potential electromagnetic follow-ups. These signals test general relativity in extreme gravity. The in-spiral merger and ringed on each encode curvature dynamics. LIGO verified Hawking's area theorem to within 5%, confirming the final horizon area exceeds the sum of progenitors. It has also constrained alternative gravity theories, ruling out certain deviations at parts in 1,000. The mergers reveal second-generation black holes formed by hierarchical collisions. When 2 black holes merge, the product can merge again, creating objects in the mass gap ordinary stellar evolution cannot produce. G 190,000, 521 formed an intermediate mass black hole of about 150 solar masses, a clear hierarchical product. These detections prove black holes grow through repeated collisions across cosmic time. Gravitational wave astronomy now provides a direct census of black hole populations independent of electromagnetic observations. The events show black holes are not isolated endpoints but dynamic participants, merging and assembling into larger systems. Each detection adds a measured mass and spin, building an empirical map of formation channels. All the gravitational wave signals we have analyzed describe the exterior, masses, spins, and final horizons. The interior stays silent, yet the mathematics of black holes opens doors to ideas that would transform our understanding of reality if they prove true. In 1935, Einstein and Rosen discovered a solution connecting two black holes via a tunnel, now called an Einstein-Rosen bridge. In its simplest form, the throat collapses before anything crosses. Keeping it open requires exotic matter with negative energy density, something that violates known energy conditions. Small amounts may arise from quantum fluctuations in curved spacetime, but sustaining a macroscopic wormhole remains beyond known physics. Other solutions treat black holes as gateways to other universes. A rotating Ka black hole contains a ring singularity. Travel through the ring could theoretically connect to a separate spacetime, a baby universe disconnected from ours. These are mathematically consistent solutions of general relativity, but they assume exact symmetries that do not hold in realistic collapse. They remain theoretical constructs. In 2013, Maldacner and Susskind proposed the ER equals EPR conjecture. It posits that every entangled pair of particles is linked by a non-traversable wormhole, implying that quantum entanglement and spacetime connections are the same phenomenon. If true, it would unify quantum mechanics with general relativity and suggest spacetime emerges from correlations. The conjecture is not directly tested, but it has reshaped how physicists think about quantum gravity. These ideas push against the boundaries of testable science. We search for wormhole signatures in gravitational wave data, such as post-merger echoes indicating a horizonless object. No such signature has been confirmed. Until we can probe the interior, wormholes and other universes remain logical extensions of equations we trust, waiting for a breakthrough. That breakthrough remains elusive, but the weirdness we have covered, wormholes, alternate universes, and entangled spacetime, shows how black holes challenge our understanding. They are one of the greatest puzzles in physics. These ideas push us to think beyond the known, to wonder what lies at the true edge of reality. What aspect amazed you most? Comment below, like and subscribe to continue the journey.